Forward to this computer this time. Okay. I think I'm recording. Yeah, okay. All right. Welcome to the module 1, or actually module 2, because our first week was really on introduction to data, the kinds of data that we have. And that's why you actually see in the main page, I'll stop the share so you can see me speak. That's why you see in the main page, actually, the front page, you saw that course map. If you're ever feeling a little bit lost, look at that course map. And in fact, I'm going to revisit that pretty much at the beginning, at the end, and at the end of each section that we hold, just so you can keep your bearings straight, so to speak. So let's take a look at that, see where we are, not just in terms of homework assignments, but also what is it that we're learning that in the context of the broader architecture or arc of the class. Someone yesterday had asked, do we need advanced mathematics or anything like that for the class? And the answer, of course, is no, you do not need that. You need some critical thinking skills, but we don't ask for anything other than some basic arithmetic. 1 + 1 = 2, subtraction and division. Sometimes we'll ask for square roots of things, so you'll need to know like the square root of 4. But really, we have machines to do that. They're called calculators. So you won't need to do any of that kind of grunt work on your own. It's really about thinking. The machines really do a lot of that for you, and that's a blessing and a curse. We don't want automated statistics, right? We'll talk about automated statistics when we talk about machine learning, but one hopes that is, if it's not supervised, at least we have algorithms that have some sort of intelligence behind them. Of course, that's quite debatable. Nevertheless, even machine learning, unsupervised or supervised, algorithmic statistics still depends on the basic concepts that we're and when I say basic, by the way, I mean elemental, fundamental. These are concepts that we will use forever. If you could, just be sure to mute your audio, just so you don't, unless you want to be a part of the conversation. Go ahead, but sometimes you don't. I was just talking about, when I say basic, I don't mean to suggest that this is easy, but that rather these are concepts that are the foundation. It's the foundation for all that you will learn no matter where you go. So if you're going into journalism, you'll need this. If you're going into data science, if you're going into machine learning, if you're going to work for Google, you still need to know statistics, because statistics is all about taking what you have at hand, the sample, and describing it, and then inferring from that sample to something outside of that sample. That's what inference is. So with that idea, with that conceptual distinction in place between description of the sample at hand or of the data at hand, and inferring from the data to something else, something larger, I'm going to explain to you how to think of these first couple of weeks, and in particular everything until the midterm, as a kind of foray into descriptive statistics. We want to know what it is our sample says. So I'll reshare the screen. You should go back and you should see the course map here. This is the first slide of the lectures. Unless I shared something else, maybe I shared the whole screen. Oh, here it is. You see the description here. These are descriptive statistics. What this really simply means is that while we're not going away with descriptive statistics, we are actually taking descriptive statistics, which is extremely useful, and then we're using those descriptive statistics to understand how we can describe the population. So we're going from descriptive statistics to inferential statistics, and that is essentially the latter half here. If I can annotate it all, this is sort of this half right here. This is the inferential statistics right here. And if you notice, these are very analogous. I know this is chicken scratch. I feel like I probably wouldn't even qualify for the Super Bowl. But if you look at categorical data, our weekend categorical data, we're really focusing on how different categories differ. And that might be, we could sort of think of that as a test of proportions analogy here, because there we're doing inferential statistics about categories of data. When we talk about means or averages, we're talking about how to infer averages or descriptive numerical statistics. Well, that's analogous to this week here. And then we can look at relative risk and odds ratios. We basically do a little bit of that when we do tests for contingency. It's the same kind of structure of data. And then when we look at correlation analyses, we see that here in our last module. We see inferences for correlation and regression. And then we also see it here, inferences for correlation and regression. If I can mark that up, well, I seem to have lost my way, but I think you can see where I'm getting at here. The main point being, you're not going to let go of these concepts, but these concepts are useful for, in essence, understanding, there we go. That's a little bit easier to read, right? I think this is useful. I wish I had done this earlier in the semester, but if you think about each of these should be little arrows. The point is that aside from a few of these introductory sections, so for instance, in the second half, we have two weeks on sampling distributions, the logic of inference. Well, if someone could mute their recording, I just want to make sure that is, just make sure your audios are muted so everyone can hear me speak. Our introduction to data is kind of our foray, our foundation for descriptive statistics, because to describe data, you have to know what kinds of data are available. Well, before we talk about inferring descriptive statistics to something that does not exist, that does not yet exist, by does not exist, I really mean does not exist within our framework, is not available to us. We need to understand what descriptive statistics are, and we need to understand what is the mathematical foundation. When I say mathematical, I mean really conceptual foundation for understanding mathematical inference, and it's really cool. It's very powerful. It has some limits though, but it's really interesting. So today we're going to talk about categorical data, and I'm going to run pretty quickly through the code because I'm going to post another section that I've done in previous years that goes in much greater detail on that. But I want to actually incorporate the readings so that you better understand how to read and understand and interpret the graphs. That's crucial for the problem sets and for the midterm and for the final, and also for the final project. You need to know what these figures mean, not just if you can cut and paste code. That being said, I'm going to next show you the code. But with that little introduction, that's the most elaborate I'll be probably. Are there any questions about what I would perceive to be the architecture of this class? Okay, advance apologies for that. So on this, this week, this upcoming Thursday, we're having we're going to have do our first problem set, which is in fact a descriptive analysis of the Titanic data set, a very famous data set. And I'm going to show you that code that we provided from class. It looks like we do have a question. So someone had asked, this is a sort of procedural question, are all the sections the same or are they different? Well, whenever I teach a section, you can guarantee they're different. We have another person on board, and typically while we haven't planned it out, I can guarantee you that each section will be different in its own right. So the way I am approaching this this course is, in addition to the nuts and bolts of programming, which I have available online, if you go to the R tutorials page, you'll see plenty of material there. I essentially break this down into two components. The first component, the first section, I focus on coding, evaluating the code. And this is analogous to the student's guide to R material, as well as the homework assignment. So it's more about understanding things from a coding perspective. And the second part focuses more on, how do I put it? The conceptual issues, the conceptual themes that are beneficial for basically for acing the class. Yeah, in terms, so someone said, well, basically two, coding and conceptual. Sure. I don't like to say that, make that a bright distinction because, or a crisp distinction, because coding is conceptual. And as we're going to see today, I'm actually going to combine those two. I'm going to provide coding and concepts at the same time, because that's, because last week we covered a little bit more material and you had to get R installed. So there's some basic sort of getting the ball rolling stuff going. But yeah, basically that's how I sort of approach things. In terms of my colleagues, I think they have other approaches as well. I think it behooves you to attend as many sections as you'd like, find what works, or if you cannot attend sections, watch whatever videos work. I post everything on YouTube. I know YouTube is controversial, but and I know it's not accessible to everybody, but there are workarounds. But what's beneficial to that is A, there's a transcript, typically. B, there's a playlist. C, you can play it as fast as you want. So you can play it twice as fast if you don't want to hear me drone on. I know some of the previous sections I've had or tutorials I've had are somewhat long. And finally, they're a playlist, so you can review them as many times as you'd like. So don't think of it as like a first pass. So I would take it, I would drink it in. I think that's the point I wanted to make before, was that you can attend any section you'd like. It's whatever works for you. And if you ever have any questions, of course, feel free to reach out to us. That's what we're here. If you want to meet individually, that's what we're here for. So that being said, ask me questions. I know this material. I can teach it, but I prefer your feedback. So, any other questions? Okay. Let's get into the RStudio interface. And if you're still not comfortable using R, which is understandable, check out the R tutorials as well. Check out the next section that is going to be posted. It's technically not within 24 hours yet. Well, I guess I surpassed the 24-hour mark. Mea culpa. But I will post the second video. In that first section that's more coding, talks about the R interface. Yeah, exactly. So someone said, yeah, I like playing at 1.5 times. There you go. If you double it, I think it's quite fast. But you might want to do that for some sections. Regardless, whatever works. You can also do it on your iPhone when you're commuting, right? And by the way, I know someone on the Stats is Everywhere thing mentioned this. I'm going to advertise the Canvas app. If you can go to your iTunes store, here's my iPhone. I don't know if you can see it. I actually have the Canvas app. So if you have the Canvas app and you subscribe to the YouTube channel that I have for the course, then you can basically, if you download the YouTube app, then you can watch the YouTube tutorials and sections that I've posted on the website. and engage in the discussion during your commute. Now, that being said, you may not want to do that during your commute, but just sometimes mobile technology works. I just want to emphasize that. Yeah, I don't know if we want to see everything at twice the speed, but anyway. Okay, so let's open the RStudio interface. So right now you see my my version of a, I don't know, I feel like this is like a Eagles versus Pats chicken scratch here. Let's stop this share, and you'll see my mug shot, and we're going to do a new share, and we're going to take a look right at RStudio. Well, look at this. So I'm not sure if you can, could someone let me know, are you able to see me while I'm sharing the screen? I don't know if you can actually see me. Okay, cool. All right. I have like unpinned windows everywhere, so I'm not sure. Okay, as long as you can see me, I think I don't know. I'm not a deep fake. There are no neural nets that have faked me yet. But what I want to show to you here is this is what your workspace should look like if you follow the previous section that I have for this mission rather. And that's because in the first mission, or in the first section, sorry, I covered how to basically, in French cooking terms, how to get your mise en place. What does that mean? Well, there are a lot of underlings, sous chef in French cooking who will basically cut all the onions, cut all the I don't know, the peppers, and then put them in nice little bowls. So that way when the celebrity chef comes on TV or whatever, they'll have everything, all the spices and everything ready to cook. That's your mise en place. Well, that's what we did for part of yesterday, was basically get our setup, have your blank slate, have your mise en place, so that way you can just select all of this code right here, which is, I'll do this again. See, it's already highlighted. I just clicked run literally a few minutes before section started. And I'm going to actually erase this pane right here. I just did a keyboard shortcut. That's on a Mac, it's Control L. But basically, no, I'm not going to hide that object actually. If we just clear everything in the panes output, we just got rid of all of our outputs. Let's pretend like and let's get rid of that tab. Let's pretend like we did what we did yesterday, which is our mise en place is we have our scripts loaded, which is our .r file. We have, we could remove that object here. Oh, whatever. See if that works. Yeah, okay. I just want to remove all the objects, everything in our workspace. So all we have left, and we'll even clear our stupid history. I want to clear everything. This is what it should look like when you open R and you open through the drop-down menu. I encourage the drop-down menu at first because this takes some practice. Your script and your, did I erase the, oh, I did. Oops. I actually erased the data set. That's okay. I'm going to use the drop-down menu, and I'm going to open that file again. The reason I encourage that is simply because it's easier to find. But you'll see a relative path file here. That's what a relative path file simply means. That's the history. I'm being silly here. Okay, I didn't need to reopen it. See, here I am doubting myself. This is what it should look like. The mise en place, that means everything is cooked, ready to order. You don't need to do any thinking at this point. You are the celebrity chef. What I mean by that is you have RStudio open, you have your data set open, you have your script open, you pressed, I think select, what is it, command, on an Apple it's Command A, I think, what is it, Control A or something like that on a PC, I forget now, I went from PC to Mac. But you should have that, essentially. So let's highlight all of this script here. I just press Command A and it highlights blue on my machine. You'll see that my lines are a little bit different because I made some notes here. But you see the script here. We're not going to worry about understanding that script because what I want to focus on today is what we asked you to read about in pages 43 to 48 of Open Intro to Stats, which is understanding graphs and tabulate and conditional whatever cross tabulations, and in particular understanding why we don't like pie charts and why we love mosaic plots as statisticians, because you're not going to know much about mosaic plots unless you've been working in stats, because it's not that common. I think if someone else might have sent me so are you saying you haven't gotten to this data set before? Oh, that's totally fine. Okay, I'm sorry. I didn't mean to. Okay. Does anyone have any questions about what's going on? I wanted to preface this week because basically for each week, for each mission, you will have a data sets that we provide for you and our code that we provide for you. And we basically do that because we want to introduce for you kind of the new concepts that are rolling out. And that's always in part 2 of each problem set or each mission. I'll interchangeably use mission and problem set. So part 1 is concepts without reference to the data, but with reference to R-like outputs. You really want to understand what the output looks like. Part 2 of the problem sets will ask you to download the script, download the data set, and then run the script, and then interpret the output and the figures. The output will be in this console pane in the lower left-hand corner, and then the graphics will be in this plots pane. Not the files pane, but this little plots pane. Your interface might look a little bit different, but typically there are 4 panes within RStudio. These are pinned, so you're kind of in a little box here. But what will always load is the script in the upper left-hand corner, or the script in one corner, which is basically your recipe. It tells you what to do. Notice I'm using a lot of cooking references. It's probably close to dinner. But what I'm trying to emphasize is that the data sets, the code for each mission are provided. And we do that because we want you to learn interactively. Obviously, I'm going to show you how to do this simply by preparing your environment, right? This is your working environment, your sandbox, your kitchen, your whatever. And then you're going to run the code. And we've made it pretty easy for you, okay? We've made it almost as easy as possible. I feel a little sheepish about this. There are no tricks here. I'm going to click run. And as long as everything works, voila, here we have a bunch of stuff coming out. Well, what is this? Well, as I described earlier, I should close that because I double ran that. Our graphics are in the lower, or in the corner under the plots pane. We have in our console the numeric output. The numeric output is going to be always a different color than the others. You'll see here in mine that's black, as opposed to the commands that I've run, which are next to these little chevrons. Well, these chevrons are essentially kind of like if you were to use like a DOS or, I don't know, terminal in Mac. This is basically to show to you, the viewer, the statistician, the new programmer that, okay, we're waiting for something else if you want to type another command or if you want to type another comment. Right? I typed a comment there by adding a little hashtag before. But if you want to add another command, you can do that. And you can do that interactively. What's basically sine qua non. If you want a job in statistics or in data science, people will want to see this. They'll want to see your script. We provide this for a couple reasons. I think the biggest reason is that so much of statistics that is most difficult is interpretation. It isn't necessarily about learning the programming language. This is not a programming course per se, although it'll be good for you because you will be able to say on your CV that you now know R. It's pretty good still. You know, it's in competition, steep competition with Python these days, but you know, R is still used ubiquitously, especially among statisticians, and R is useful for so many reasons. You don't want to go into the programming wars. Just basically learning more programming languages is useful, but the point I want to make is programming languages change. We saw this in the installation issues. A lot of students had difficulties that arose from a change in the code, underlying code from last November. So before the beginning of last term and now in this term, there seem to be some changes, perhaps some bugs even. So this isn't a programming course.
It's 5:30.
Sorry, that's my own not so smart intelligence telling me what time it is, if you heard that. We don't need that, but it is a good indicator of where we need to be going. So you see the code up here, and as I mentioned before, I'm posting a tutorial that explains to you what how to understand these concepts in greater detail. But what I want to emphasize, I want to emphasize aspects of the interpretation that are far more useful for the course, for succeeding in the course. Basically, it has to do with interpretation. You will see output like this. If you haven't done the mission yet, you'll see output like this, where we might have a question like this. Based on this data set, right? This is the Titanic data set. This is a ship that sank infamously. And using the categories available, which is survivor, ship, whether you survived or not, and your gender, whether you identify as male or female, what proportion of men survived the Titanic approximately? Well, this requires you to understand what kind of tables we have here. Here's basically you could say this is a contingency table. And that's the first kind of output that we have. We basically understand or do a lot of interpretation of categorical data using contingency tables. And then we also look at them using this figure on the right, bar plots, or bar charts rather. My R lingo's getting ahead of me. And a contingency table, as it might sound, tells us the proportion or the percentage of one category contingents on splitting the sample by another category. So what question 12 insinuates, and by the code as well, that it basically insinuates that, or implies that if you were to divide the sample, or the passengers rather, it's not a sample because we don't have a population to infer to, right? There's only one Titanic. We're describing one singular event. If we divide passengers into male or female status, among males, what proportion survived? Among females, what proportion survived? And that's a two-way contingency table. And we know this as well. We know this for a couple of reasons. First, we know this from the syntax because, as I mentioned in a tutorial that's coming, this little vertical bar or pipe is kind of a syntactic version of telling us what a contingency table is. But you may not see that, and you probably won't if you're reading and consuming statistics. You're going to see something that looks like this. maybe probably without these ones at the bottom. So the thing we have to know or understand is that a contingency, this is a contingency table, and you should be able to, not should, but it behooves you to view this in the blink of an eye with enough experience, that with the knowledge that this is a contingency table. And you can know this without these ones at the bottom. Well, what do these ones mean? These ones mean that if you split the sample into two groups, and then you basically take the you divide, you understand the other, you take the sample into two groups, you basically have two groups that are separate entities. And so among males, whether you survived or not, the proportion who survived and the proportion who died in the Titanic among men, that proportion will equal to 1. If you're female, then the proportion of females who died and the proportion of females who survived is also equal to 1. So within the R environment, these ones at the bottom, right here, you'll see this here, and you'll see this here. Those are clear indications that we basically split the sample into k number of groups. K meaning as many other categories as we have. So for social class, we split the sample into 3 groups, and then we looked at the proportions of survivorship within each group. So I think that's important to understand with a contingency table. And the way I remember it is contingent on what? Contingent on being male, what is the proportion of survivorship? And here, the decimal places are putting it out of the way, but you'll see that for men, surviving is 0.21. That means 21% of men on the Titanic survived. And then for females, survivorship is 0.75. So that means 75% of female passengers on the Titanic survived. Okay. So there you go. And if you want to look at bar charts here, oh, we go to class. We haven't really done that yet. Well, I don't want to start with that ugly pie chart. Then we'll go to the sort of the big question here, which is a kind of a classical, relatively famous finding. People ask, well, does class matter? It's a Marxist concept that class matters. Gosh, you know, it doesn't matter whether you're poor or rich. Well, if you're on the Titanic, and if you haven't seen the James Cameron film, sorry to break it to you, but the ship sinks. But even more interestingly enough, class matters, right? So it was not just a probabilistic statement that the person in third class, our male protagonist, died on the Titanic, although that's just a fictional story. It statistically was true. History has shown that class is associated, at least as far as we can tell, class is associated with mortality. In what way might you think? Do you think the upper class, the low middle class, or the lower class differ by mortality in ways that are counterintuitive? Do you think money would help you on this boat? Well, look, it does. Because among those people who were in the upper decks of the Titanic, the elites, where the elite meet to greet, 64% of those survived. Those in the middle class, still not as fortunate, but 44% of the middle class survived. And then in the lowest class, these are the the people who are in the who have the least economic means to survive. 26% of those survived. This was published, as I said before, I think in Science, but it's a good example of a contingency plot that provides really powerful evidence, and evidence that is important for, as we talk about in this mission, the field of cliometrics, which is quantitative history. It's becoming increasingly common as we're digitizing documents and refining new archives, that history can be quantified and we can understand very particular historical events simply through descriptive statistics. We don't need to infer to a population here. We're actually describing a singular event. So descriptive statistics are in fact important. Quite often we're interested in what makes this event unique rather than what makes this what does the entire population think as a whole. If you could, thank you. Okay, so we do talk about visualizing categorical data, and I realize I only have a few minutes left. I'm kind of vacillating whether or not we should stick with the Titanic data because it's relevant for the assignment, or whether we should go to the readings. I want to point to the readings very quickly, only as a, if you could please mute your mic, thank you. If not very briefly, just so you can get an idea of the kinds of graphs that would be available and why we don't look at pie charts. I'm just actually going to show you one page. This is page 48 from the open intro reading. So this is my little disquisition on why we're not using pie charts and why you're going to see them. And in turn, why are we looking at mosaic plots? And then I'm going to focus the last 15, 20 minutes on interpreting and understanding a mosaic plot. So let's take a look at that. I'm going to stop the share and I'll add a new share. There we go. So this is page 48. As they say rather facetiously, the only pie chart you'll see in this book. Well, it's really fascinating, right? If you go work in business, if you work for funders, if you work in at any interface within people outside academia, pie charts are kind of our lingua franca. I've worked and presented pie charts before. But what's the problem with a pie chart? Well, the problem is if we have categories and we want to know, we want to compare those categories, then statisticians really like bar charts because you can see the differences in those categories. And you see this right here. We don't need to know what these categories are here. But basically, as they say, it is generally more difficult to compare group sizes in a pie chart than a bar chart, especially when categories have nearly identical counts or proportions. Well, these two are identical. But what it really does is it sort of masks this great magnitude of this blue category right here. And that's the advantage here. You can basically look at magnitudes much more easily. Here, you're constraining everything to actually a fraction. You're standardizing it, but it's also just hard to see, you know. Try to pick up a pizza and just take a look at, well, remember the last time you picked a pizza slice and maybe it wasn't, you ate too much pizza? Well, maybe because it's hard to judge the size of a pizza slice. I don't know. But you can, I hope this clarifies things here, right? It's much easier to see that. More generally speaking, if you notice, I showed you those contingency plots, the conditional contingency, two-way contingency plots. Well, numbers are okay. They give you legitimacy, right? Especially if they're intimidating to a lot of people. But if you look at this, the other issue, I think, and this goes a page beyond what we're talking about, and we'll talk about some of these graphs here. The reason we're so interested in effective graphing is that it's so much more effective. You can take a look at these numbers. My eyes are already glazing over. But look at this. Well, now you look at, basically, if you look at this left one, these are box plots of a numerical variable. And I don't think we go to box plots today. I want to make sure that we don't do that. No, we don't do that, because those are numerical variables. But the point is, if we're comparing two categories by a numerical variable, graphing makes so much more sense, right? You look at a quantitative distribution here, you can see so much more, and that's here. You can do this, and you can have this table, and you'll get published in the mainstream economics journals, right? But you won't see this. And that's a huge cultural difference within statistics and academia as well. That's what I want to say here. And then that's why we go to these things called box plots. But I do want to say that, I'll spend 5 more minutes on the anatomy of figures here, because I think this is extremely important. Let's not focus too much on the content here. But one point I want to make here is that another advantage with bar charts is you can stack them. Here you have a variable, categorical variable with 3 categories, right? We could pretend this is like low class, middle class, or high class. And then you have a count. This could be the count of number of passengers or whatever. Well, basically what you can do then is you can count the number of items or observations and stack those that belong to each category. Right? So if we did this with survivorship or not, we could say, well, what are the number of passengers who died and didn't die if they're in lower class? Those who died and didn't die in the middle class. Those who died and didn't die in the upper class. You can't do that with a pie chart. So it provides an additional framework for comparison. Figure B on the right is simply standardizing the x-axis. So it is a proportion. That gets us quite close, by the way, if you think about it, to the contingency plot that we had when we looked at the proportion of mortality and social class. Social class is here. So the main difference here is that this is standardized, which means that it goes from 0 to 1. It's expressed as a proportion, right? What proportion in the lower class survived and didn't die? That could be 2 different colors. What proportion died or did not die in the middle class? 2 different colors. What proportion died or did not die? That's the upper class. So there are 2 different ways of expressing bar plots or bar charts, either as stacked bar charts of the counts by of those who died and didn't die, or as proportions that are stacked. Well, we can remix this a bit more, and we can express this as a mosaic plot. And this, by the way, on the right is pretty close to getting to a mosaic plot. But I'm going to talk to you what a mosaic plot does. They're going to talk about emails and this kind of stuff. I'm going to go to this example, and then I'm going to go back to the survivorship data and take that contingency table that we had, and then I'll show you what that looks like and give you an interpretation for that. What we're doing here is, if you could please mute. I'm asking those of you to mute. Okay. What we're doing here is first of all, we're dividing the sample by the proportion of those who belong to one category or not that category. And that proportion is proportional to the length of that the x-axis, where I'm going right here, the horizontal axis. So that means that about 10% of this sample is not spam. Oh, sorry, 80% or 90% of the sample is not spam, because that's a very long, that's about 90% of that length of that x-axis. And about 10% are spam. Well, we do the same thing with the y-axis. Among those, notice I'm saying among those. That's a key word, by the way, for contingency tables. Contingent on being in the spam category, which is only 10% of the full sample, as our x-axis shows, we see that this green category is quite high. We see that the blue category is not as much, and the red category is equal to the non-spam right here. What we see here is the same thing. You're basically scaling representing the second category in terms of its proportion within that group. So the y-axis will give you proportions conditional on the category that we divide the sample into. So it's a conditional probability, right? So we have a conditional probability on the y-axis whenever we look at a mosaic plot. It's called a mosaic plot because in standard English, a mosaic is I think it's a type of design in art that has kind of nice pattern squares. You'll see them in, I think, in a lot of some of like really nice art in some of the mosques in Spain, for instance. Nice tile work. It's supposed to have sort of a visual appeal. That being said, it's not used really outside of statistics, but we like it more. And let me show you how this might be useful. And my caveat is you don't have to like this, but you do have to understand what a mosaic plot is because you're going to be tested on it for the class. So let's take us back into the world of R. And we're going to go back to these plots. I'm going to just loop through this script because it looks like, well, did I go to the last plot? Okay. So here we did a pie chart of the proportion of belonging to lower, middle, and upper class. And here we have our mosaic plots where we show what survivorship is conditional on social class. So what this does is it's effectively a figurative or graphical representation of this right here, what I'm highlighting over here. Let me see if I can annotate this. I'm going to just put this right here. What you can see in numbers here is actually represented in this mosaic plot. So what we see here is in the upper class, you actually have a relatively small proportion of that sample belonging to the upper class. And actually, I'm going to clear this because you can see, first of all, that the upper class, let's interpret the mosaic plot in two ways. First, let's remind ourselves, just focusing on the x-axis, the horizontal axis, we're thinking about these widths of these lines as a proportion. So about half of the sample belongs to the lower class, about a quarter of the sample belongs to the middle class, and about a quarter of the sample belongs to the upper class. What that means is we're basically assuming that the whole sample, I'm going to clear all my drawings. I'm going to get a better drawing stick. We're basically assuming that the entire social class consists of some sort of line here. And then we're basically saying, okay, given that that is the case, let's divide that into groups proportion on their size. So, okay, well that from right here to here, that's the lower class. And then from right here to here, that is the upper class. That's a little bit lower, but basically we have 25% of the sample here, 25 here, 25 here. And you can tell that because if we go back to our previous pie chart, that's what the pie chart shows. Well, okay, the pie chart is really just the horizontal axis of the mosaic plot because it shows us that half the sample is about 0.25, about 0.5 of the sample is 50% of the sample, or 0.5 of the sample is in the lower class, 0.25 is in the middle, 0.25 is in the upper. That's all so all we're doing with the pie chart is we're taking a lot of ink and giving us very little information. It's very low information material. Reminder, I'm hearing a little bit of scratching or something. Could you please make sure you're muted unless you want a cameo? So then what we do here is, remember, let's go back, revisit our two-way contingency plot. Well, in our upper class sample, 63% survived, 36% did not. 64 versus 36. So about 64%, over half, should survive, and that's what that shows, right? This is about 65% of that sample. Okay, in the middle class, about a little less than half survived. That's what we see. And then in the bottom, we see only about a quarter of the lower class survived. So if we look at this y-axis, we can see, okay, 1, 2, 3, 4. Okay, that's about 25% of that. So here we see 25% of the lower class, 44% of the middle class, 64% of the upper class. And this is simply a way of representing the two-way contingency or multi-way contingency table, right? 3x2 contingency table, to represent categorical data in a way that's much more information dense and also gives us a relative magnitude that is much more informative. It's not a bar chart, right? It is not a bar chart because the width matters here as well as the height. A bar chart, if we can go to those, the width doesn't matter, right? We have counts of survivorship by those, but there's no width here. You have two groups, and then you just have the number who survived within each group. And that gives you a pretty good magnitude, I suppose. But when it comes to information dense material, this is pretty compelling because it gives you some insights that you might not see from you definitely won't see from the pie chart, but you also probably won't see from, proportions or anything else that is simply just like even a bar chart. Well, what does it tell you? It gives you a sense of the relative proportions of mortality. It gives you a sense of the relative distribution of those categories that expose you to increasing risk of mortality, right, being in the lower class. But it does one third component that is not readily maybe apparent, which is it shows you by the area of each tile in the mosaic the relative size, right? The relative size, the joint probability, you could say, of belonging to two categories. So not only gives you conditional probability, it actually gives you joint probability. I'm sorry, it does not give you joint probability. My bad. It doesn't do that. Well, no, actually it does, because no, I'm sorry, I'll take that back. It does, because it gives you the relative size of the relative size of each population, either exposed to the risk or not. So, for example, we can see that the greatest number of passengers were in the lower class, and they're the most likely to die, the least likely to survive. That means the biggest risk group was the largest group were those who were not survivors and those who were in the lower class. The smallest group in the entire set of passengers on the Titanic were those who did not survive but were in the upper class. What it also shows you is that while the risk of mortality is very high in the lower class, because the lower class is so large, the number of survivors in the lower class is equal to or even might surpass the number of survivors in the middle class. I mean, just take a look at the relative sizes of those tiles here. This is a rather oblong tile, and this is a rather, a square tile, but they give you an indication of the relative size of each group as defined by the intersection of two categories. And I guess the last point I'd make, which is it's a bit prosaic, but the point is that while there are risk factors, and while there are factors that lead to increased probability of something of an event to occur, probability is not destiny. You can be in the upper class and you can still die. On the Titanic, you can be in the lower class and you can still survive. So there is even chance. One might say there isn't always chance, but the point is life can be a roll of the dice. Not to be a little too moribund here. I know we spent quite a bit on the mosaic plot, but I think that's one of the most confusing concepts in the course, to be honest, other than when we talk about joint probability, because no one sees this. Someone is asking, how did the Mosaic find the width allocation from the data set, width of lower versus width of middle versus upper? I'm not sure what you're asking here, except to say, I'm not sure what you're saying here. How the Mosaic? Well, the Mosaic doesn't find anything, right? It's an algorithm. It's a machine, right? But what is it? It's basically it represents row proportions. So what it does is, what does it do? It takes the proportions within one category, represents those into proportional segments of a line. So you just take, okay, in the same way, how does a pie chart work, right? A pie chart represents the proportions as relative sizes or slices of a pie, constrained to a circle. Well, we're constraining to a line the relative proportions of the univariate categorical distribution of social class. So that would be, I think we see that in a pie chart somewhere else. Maybe we don't. So it does that, and then it gives us the contingent proportions given you're in a particular class, and it constructs proportional lines based on of survivorship based on your probability of survivorship within that class, and the rest of it is just graphics. How is the x-axis split contingent and proportion is easy to understand? Well, not necessarily, right? Contingent and someone just had a really good question about contingent versus disjoint probability. It has to do with the numerator. Contingent proportioning. You want to say proportioning, right? How is the x-axis split? Well, in the same way that you would split this right here. But let me give you a better example then. I think this might be easier to understand. Here, I'll show you. And forgive me if I'm not giving you the best answer, but let's see if this works. I'm going to do a new share, and I'll show you just from the readings, and I would recommend you. You see that? Yeah. Okay. So here we have the readings. I skipped ahead of this, but basically, let's take a look at this example of the one variable mosaic plots right here. What does this mean? Well, it is simply the graphical representation of that bar chart we saw up here, right? One large and two smalls. If I can go up here, one large and two smalls. Well, what'd you do here? One large and two smalls. So how did it do that? Well, it basically took the proportions for each of those, and then right here, if you take a look at this one graph on page 44, you look at the proportions. You have two equal small proportions, and you have a large proportion. These are each represented by a number, right? This is about 0.2, 0.2, 0.6 something, so it's more like 0.15. 0.15, 0.15, 0.7, you could say. That equals to 1, right? Proportions, you add up three proportions of three categories, they're going to equal to 1. That's why I emphasized the 1 before on the contingency table. And if you do it just a one-dimensional, one-variable contingency table, you have this. Well, that's not that interesting necessarily. I mean, it kind of is, but only if you constrain your eyes to just that one little horizon right on the x-axis. That's what A shows you. Is that a little more intuitive? So that's non-contingent univariate variates. It's one variable where you slice up the cake. Now we're going to cakes. You're going to slice the cake according to the proportion of survivorship. right? Next time you bake brownies, you could even do this. That'd be a really cool experiment, right? Draw a line, figure out the decimal place, the proportion of survivorship, cut those lines, and then within each of those categories, you're going to take the next side of the square, and you're going to cut that based on your contingency table. Well, okay, among those in lower class who survived, oh, about 25% we're going to cut here. And then in our Titanic example, among those in the middle class who survived, about 44%. If we're doing a cake here, we cut it right about here. Okay, among those in the upper class who survived, well, gosh, I think 75%, we're going to cut that last piece right up here. So basically what you're doing is you're taking a univariate proportion, unconditional proportion of one variable, splitting it up, and then within each split, you're going to split it by each contingent proportion. Split, split, voila, the mosaic plot is right at the bottom. Does that help illustrate that? Two new messages. Oh, I need to get to my pointer here. Good, okay, thank you. I know it's not, here's the thing, I know it's not easy, but I recommend rereading those portions, rereading those sections. I think that's helpful. And here's what I would remember. And I have had trouble remembering this because it's not that common that I've run into this. In academic papers, I've been told, oh, we can't afford to publish graphs. If you want ink, you gotta pay us $6,000. And besides, it's not scientific unless you have numbers. Well, that's silly because then you can't see what's going on. But this is what I have often forgotten, but I don't want you to forget. The horizontal part of that square, we'll use my brownie analogy. I'm a fan of that. You're going to take and cut whatever it is you want to be conditional on. However, you're going to divide the sample. That's going to be your y-axis, your x-axis, your horizontal axis. Do that first. It's unconditional. And then your x-axis is going to be conditional. Your splits are going to be conditional on that. So there you go. Maybe that'll be a viral YouTube video. Brownies and mosaic plots. Okay, so I hope that was useful. We went through most of the figures. I think we went through most of the instrumental parts. I think the rest of it's relatively self-explanatory. That being said, I'm posting a video that's a tutorial that goes in greater detail about what these functions are. You'll see the tally function. You'll see like a little tilde, squiggly line. You'll see what I said. It was the vertical bar. Those are details. What I really want you to do is to know what a mosaic plot is, explain it to your friends, and have a debate about pie charts. Unless they're paying you, of course, and then no. Because a lot of people love those pie charts. Okay, thank you very much. Feel free to contact me, as always. Here, I'll type in my email, of course. Don't be a stranger. And, of course, oops, I'm sorry. I did a private message here. I want to type everybody. I'm not very successful there. Okay, well, one of these days I will send you my email. If not, go to my first introduction. I give you a link to my profile within Canvas. Otherwise, great to see all of you, and I hope to hear from you soon. And I will